In this fourth part, we move from multivariate vectors to functions, fields, and stochastic processes observed over space or time. Many applications of extreme value theory are not naturally finite dimensional. We may observe a spatial or temporal field, for instance, rainfall over a region, temperatures over time, wind speed over a geographical area, or losses evolving along a time window. The first point is that extremes often occur over regions and time intervals, not only at isolated points. A storm, for example, has a spatial footprint, and a heat wave has a temporal persistence. The second point is that we often care about functionals of the whole field. This may be the maximum over the region, or the total accumulated impact over space or time. The key questions are therefore, what is the limit of pointwise maxima of random fields? What is the limit of functional exceedances? And how can we quantify extremal dependence over space and time? We now consider independent copies of a random function, for instance, a continuous curve on an interval. This is the functional analog of a sample of random vectors. The first object of interest is the pointwise maximum process. At each location or time, we take the maximum over all observed functions. This gives a new function describing the largest observed value at each point. The second object relies on a risk functional. Instead of looking at each coordinate separately, we summarize each function by a severity measure, such as its supremum. We then study the largest values of this functional together with the associated normalized shapes. The third object is the exceedance count of high-level sets. Here the event is not just that one number is large, but that the whole function belongs to a set of extreme functions. Finally, high exceedances are studied through conditional laws, given that the function is extreme according to a chosen criterion. We first study functional analogues of GEV limits, max stable processes, which describe limits of normalized pointwise maxima. This slide extends the idea of max stability from random variables and vectors to stochastic processes. The definition says that a process is max stable when the maximum of independent copies, after suitable location and scale normalization at each point, has the same distribution as the original process. The normalization is now allowed to depend on the spatial location. The theorem by de Haan gives the fundamental motivation. If normalized pointwise maxima of independent random processes converge to a non-degenerate limit in a space of continuous functions, then this limit must be a max stable process. Moreover, each marginal distribution of the limiting process is a GEV distribution. So the univariate theory remains present at each point. But the process also contains the dependence structure linking the extremes across space. As in the multivariate case, it is convenient to standardize the margins. The first bullet explains that we transform each marginal distribution to the unit Fréchet scale. On this scale, each point has the same marginal tail behavior, and the displayed formula gives the corresponding distribution function. The second bullet explains why this is useful. Once the margins have been standardized, they no longer drive the differences between models. All the remaining modeling effort focuses on extremal dependence across locations or across time. This is important in spatial extremes. We want to understand whether extreme values occur independently at distant sites, whether they cluster, and how the strength of extremal dependence decreases with distance. This slide gives the central representation of simple max-stable processes. I will not read the formula literally, but the idea is very intuitive. The process can be represented as the pointwise maximum over infinitely many random events. Each event has two components, a severity level and a spatial footprint. The severities come from a Poisson process with a heavy-tailed intensity. The functions describe the spatial shape of each event. For example, the footprint of a storm. The normalization condition ensures that the margins remain unit Fréchet at every point. The storm interpretation is the key message. A max-stable process is obtained by superposing infinitely many potential storms and keeping, at each location, the largest contribution. This representation is also useful for simulation and for building parametric models. This slide lists three historically important families of max-stable processes for spatial extremes. First, the Smith model represents storms as moving kernels with Gaussian shapes. Each storm has a random center and a random severity, and the observed process is the maximum over all storms. This gives a simple and interpretable spatial model. Second, the Schlatter model is based on a Gaussian process. The positive part of a Gaussian field is used to generate the spatial footprint of extremes. The dependence is controlled by the correlation function. Third, the Brown-Resnick model is built from a Gaussian process with stationary increments. Its dependence structure is governed by a semivariogram. This model is especially important because it is flexible and widely used for spatial extreme events. Although max-stable processes are infinite-dimensional objects, in practice, we often observe them at a finite number of locations. This slide explains how their finite-dimensional distributions are characterized. The first part says that if we fix several locations, the joint distribution at those locations has an exponential form. The exponent function is obtained from the spectral process by taking an expected maximum over the selected locations. This is the direct functional analog of the multivariate spectral representation discussed earlier. The second part introduces the extremal coefficient. When all thresholds are set equal, the joint distribution depends on a single number between 1 and the number of locations. A value close to 1 means strong extremal dependence. The locations tend to be extreme together. A value close to the number of locations means weak dependence, close to independence. We now turn from maxima to threshold exceedances and introduce the functional analog of generalized Pareto distributions. This slide introduces a peaks over threshold approach for stochastic processes. We start with a non-negative, heavy-tailed continuous process defined on a compact set. Instead of defining an extreme event only through the maximum of the process, we use a cost functional. This functional must be homogeneous. Multiplying the whole function by a positive constant multiplies the cost by the same constant. This property is important because it separates the severity of an event from its shape. The peaks over threshold object is then the conditional law of the rescaled process, given that the cost exceeds a high threshold. The last line gives examples. The cost can be the supremum, the total mass, the value at a fixed site, or the minimum over the domain. Each choice corresponds to a different definition of what an extreme functional event means. This slide gives 3 equivalent ways to define a simple L Pareto process, which is the functional analog of a generalized Pareto distribution. The first characterization is constructive. The process is written as the product of a Pareto severity and a normalized shape. The shape has cost equal to 1 and it is independent of the severity. The second characterization is a homogeneity property. Once the process is extreme, scaling the threshold changes probabilities according to a power law. This is the functional version of regular variation. The third characterization is peaks over threshold stability. If we condition on exceeding a higher cost level and rescale by that level, we recover the same law. These 3 views are complementary: construction for simulation, homogeneity for theory, and threshold stability for statistical diagnostics. This slide introduces the terminology and the spectral measure associated with an L Pareto process. Such a process is also called a functional generalized Pareto process. It is designed to model extreme functions above a high threshold. The spectral process is obtained by dividing the extreme function by its cost. After this normalization, the resulting shape has cost equal to 1. The distribution of this normalized shape is called the spectral measure. It lives on the L-unit sphere, that is, on the set of functions whose cost is exactly 1. The idea is very similar to multivariate extreme value theory. We separate the radial part, which measures severity, from the angular part, which describes the profile of the extreme event. This slide makes the analogy with multivariate extreme value theory explicit. The radius is the cost of the process. It measures how severe the extreme episode is. In the simple model, this radius has a Pareto tail. The angle or shape is the normalized process. It describes the event profile. For example, whether a storm is localized or widespread, or whether a heat wave is short and intense or persistent over the full time window. The independence between radius and shape is particularly useful for simulation. To generate extreme episodes, we first sample a severity level, then we sample a shape from the spectral measure. Multiplying both gives a synthetic extreme function. This is exactly the kind of decomposition that can be useful when evaluating or constraining generative models for extremes. This slide restates the threshold stability property in function space. If the process follows a simple Pareto law, then raising the threshold in terms of the cost functional and rescaling the process gives the same distribution again. This is the functional analog of the threshold stability property of the univariate generalized Pareto distribution. The practical implication is very important. If the peaks over threshold model is appropriate, the distribution of rescaled exceedance functions should remain approximately stable when the threshold increases. This gives a diagnostic tool. In applications, we can compare normalized shapes above several high thresholds. If the distributions change substantially, the threshold may be too low, or the chosen cost functional may not capture the right notion of extremeness. The final slide connects the Pareto process with functional regular variation. The assumption is that the original random process is regularly varying in a space of continuous functions. This means that the probability of very large functions has a power law structure, and that extreme shapes converge to a limiting spectral measure. The theorem says that under mild conditions on the cost functional, the conditional law of the rescaled process given a high cost exceedance converges to an Pareto process. The final display explains how the spectral measure is updated when we change the definition of extremeness through the cost functional. In words, shapes that have a larger cost receive more weight in the limiting conditional distribution. This completes the bridge from functional regular variation to practical peaks over threshold modeling for random fields and processes.